Hello and welcome to Embedded Internals. This is 10th episode of our series, Pointer Thinking series. In this episode, we are going to debug the pointer bugs like a system engineer. In the last episode, we have seen that all pointer bugs are almost same. They points to just one thing, that there is some address corruption. So whenever you see any pointer bug, it may be because of null pointer dereference, while pointer, dangling pointer, use after free, buffer overflow, array out of bound, double free, or any heap corruption. Just ask few questions: whether the address you are trying to access is valid, whether the owner of the address is valid, and what is the lifetime of that address. Let's start by debugging all those pointer bugs in our terminal. The first bug we are going to debug is null pointer access, null crash. So this is a very simple program where we have an integer pointer which is marked as null, and we are trying to dereference that pointer. So null means that uh, we are not pointing actually anywhere. Null is 0 into 0, invalid memory. So when we try to read address 0, what will be the answer? GCC -G -O. These are the debugging symbols we have used to debug this code in uh, GDB. So when we run this program, null crash, we see segmentation fault. So when we are trying to access the dereference, the null pointer, operating system is returning back with segmentation fault. So let us debug this in GDB. So breakpoint we have set. Now run the code. Yes. Breakpoint 1, this. We have first is next line. We are trying to dereference the pointer. Just print ptr. Pointer is pointing to null address. Okay. What is the value pointed by this? Only print. This is pointer is pointing to an address null. When we are getting the value, we simply saying cannot access memory at 0 into 0. Sir, we are not able to access this memory. Let's next. Program received signal error. Signal SEGV, that is segmentation fault. And fault at the line number 7. So 7 is while dereferencing the pointer. So we come to know that why the program crash and at what point program crash, and at that point what the value is in the pointer. Okay. Whenever we see any crash, just don't start debugging without any proper flow. So we should have a workflow while debugging any crash, any memory related crash. First, by using the backtrace, by identifying the fault line, like here the fault line is 7, by checking the pointer value, by checking the memory ownership, and then at the end we find the root cause, and root cause in this case is cannot access memory at address this. Okay, so this is what happened when we are trying to dereference null pointer. So to fix this issue, just before dereferencing, point the pointer to any valid memory location, then dereference. Okay, let's move to our second error pointer bug, that is wild pointer. So this is a very simple example where we have an integer pointer and we have set that integer pointer. So we are writing to this location value 10. Okay, let's see what will happen. So this is wild pointer dot slash wild, no value. Okay, we have not printed any value, that is the reason. Let me print this value. Value is 10. So in case of wild pointer, if you remember that we have while we are discussing the wild pointer, we said that sometime we may get a value that can be valid, that sometime invalid value can occur, sometime some memory corruption. So what is the final output, we don't know. So the behavior is totally undefined. What is happening in this case? Let me print the pointer as well. When we print the pointer, the output we will get is seems to be pointing to memory, some memory which seems to be valid, but actually it is not valid. We don't know if this memory actually belongs to our program or not. The fix for the null while pointer is that whenever you allocate any pointer, just set it as null, okay, before doing any operation. The first point, always remember, whenever you are declaring any pointer, set it as null. Let me show you one more example where we are returning local value from the function. So in this case, this is an example of returning local variable address. So we have a pointer, integer pointer, which is calling the get value. So in the get value, returning the integer pointer. So in this function, we have a local variable x and having the value 10, and we have returned the address of x. So ideally the return pointer, return value should get stored in this, and when we will try to dereference the value stored at that address, the result will be 100. But as this function has gone out of scope, the function existed, the local variable which has the function scope also goes out of scope. So x is pointing to a valid memory location, but object has been gone. So what will happen in this case? Let us see. This is a classic example of dangling pointer, where the address is valid, but we don't have the ownership of that memory location. Address valid, object gone. Segmentation fault, as expected. Because memory died when function return. This is an example of ownership as well as lifetime. X is a local variable whose lifetime is function scope, right? And once it returned, we lost the ownership of that pointer. When we debug this code in GDB, we get the segmentation fault. Let us print this pointer. Oh, sorry. Pointer is pointing to null location. 14th line we get the error. This is this. We cannot access this memory address. So this is a classic example of dangling pointer, where address may be valid but object does not. Use after free. In this case, we have allocated memory to our pointer using dynamic memory allocation, that is malloc function. And in that pointer, we wrote 10 to that pointer. And after that, we free the pointer. And after freeing, we are trying to dereference the pointer. So memory has been released. When we will try to read the value from that released memory, what kind of error we are going to get? This is the most dangerous bug, because like in the case of dangling pointer, here also we can have undefined behavior, that sometime it works, sometime it don't, and sometime it works today but might in future there is a chance that we will have some corruption, some garbage value as expected, because memory has already been released. When we try to read from that memory, we are getting corruption. So in this case also, valid pointer is valid, but ownership has been lost. Recompile this code in address sanitizer, ASAN. Use this command, gcc -g -f sanitize equal to address. When we run, we get the detailed error. So shadow bytes showing the buggy address. Error address sanitizer heap use after free on address this at some point, and it is saying program counter, base pointer, and stack pointer address. So what is the error? Heap use after free. And what is the address? This. And these are the other details from the heap and stack region. So this is ASN report. Double free. So this is our fifth example. First we have checked null pointer access, then we have checked while pointer, then the dangling pointer, then use after free, and this is double free. What happens in the case you have allocated the memory, allocated the pointer, freed that pointer, and again trying to free it? How will our code will behave? So we are using address sanitizer for this also. Avoiding. No shadowing detail, just avoid it. And the reason for avoiding the this is attempting double free on particular address. So what is the reason for abort is double free. When we will without compiling it with this address sanitizer, I'm just compiling with normal GCC. It is the return. So the output is free, double free detected in tcache 2, aborted code dump. So this is the error you will get when you are trying to double free. So you will know that yes, there is a double free detection, means allocator metadata corruption, and RCA detected, we will correct our code. Okay, let's move to check what happens in case of a stack overflow. So this is a simple program where we have a character buffer having 8 bytes of memory, and using the string copy function, which is a library function, we are trying to copy hello world in this buffer. Let us see what kind of error we will get. Stack smashing detected, terminated, aborted. This also result in code dump. Stack buffer overflow at address, and the program counter, base pointer, and stack pointer memory address. So it is writing of size 12. Our buffer is 8 and we are trying to write 12 bytes of data inside it. And this is the reason for a corruption. Address this is the address where the crash has happened, is on stack of thread T0 at offset 40 in frame, and in frame buffer memory access of offset 40 overflow this variable. Okay, so this is the reason for crash. So root cause has been immediately visible by using these tools like GDB and ASAN. We can detect the root cause and then correct our code. So either we will increase the buffer size, or we will use the safer alternative of string copy. So production system may crash without debugger. That is the reason we should enable this, so that whenever any crash segmentation fault occurs, we will get the core. And core file contains the memory snapshots, registers, stacks, and process state. Heap overflow is also same. We have allocated the memory of 8 bytes, similar to the stack we have done in the heap area as well. For heap area, we have used the malloc function, and we are trying to copy hello world in that. And after copying, we have just freed the memory. Let us compile the code. what the address sanitizer tells us about this. So silent corruption. When we run this code in this, we simply address sanitizer let us know that heap buffer overflow occurred at particular address, and this is the 8-byte reason, this memory corruption error. And the error is because writing of size 12, whereas the buffer is of we have allocated 8 byte of data, even we are getting size 8 and trying to write 12 bytes of data. That is the reason for heap corruption. So this is the way we can check for the RCA why our program crash. So root cause in this case heap buffer overflow is write beyond allocation. Like in the stack we have heap in the heap area also we have same error. Array out of bound. Out of bound means we have an integer array of 3 integer elements, whereas at the array 10th location we are trying to write some value. No crash, but no output. Oh, no output because we have not printed any printf statement. But let me show what address sanitizer tell us about this. So address sanitizer don't have any information about array out of bound. So these kind of bug where we might get answers sometime is really dangerous, because we know that we are trying to access the memory which is out of bound of an array, but still we are getting the value. It means at some or the later time it will definitely going to crash, and that will be the silent crash without even the user knows. So we should be very careful while we are designing the code. Now let us see an example of memory leak. Memory leak means we have allocated the memory but forget to free it. Like in this case, I have allocated the memory and then set the memory null pointer as null. So we have memory allocated, but the reference to that memory we have lost. Okay. So memory allocated memory reference has been lost because after allocating the memory and before freeing it we have just set the memory as null. So where it is actually referring we will lost and we will not able to free it. Let us run this code in Valgrind to know actual output. So this is the Valgrind output. To run the code in Valgrind, simply use this tool Valgrind. If it is not installed on your system, do install it. So what is the summary of this? In the exit, 100 bytes in one block has been allocated. So total heap use is 1 block and free is 0. So 100 bytes allocated. Definitely lost, 100 byte has been lost. Let us run our Valgrind with full check. So summary is where we have the allocation problem, memory leak function, memory leak file, and line number is 5. 100 bytes in one block are definitely lost in record. So lost. Okay. So this shows that we have allocated the memory, but as we have set the pointer as null, we have lost the ownership of that memory. So we will not able, memory become unreachable and we will not able to free it. And at the end, after continuous running, long term running, system will become crash because memory has been kept on allocating without freeing. System slow, and at some point system crash. Let's move to our next example. This is a example where I am going to show how we can use the watch point. So this is simple example where I have an integer variable x. Initially the value is 10, then I have modified it by 20, then modified it by 50. Simple. In this code, we are just going to debug it to watch the x variable. So to preserve the symbol, I am using -g, and for optimization -o0. We get the output. Let's run this in GDB. So after running the program, we have set break at main, then run, and we have set the watch point at value x. Next. So old value is some random value 32767, because x has not been initialized, x has been just declared, and we in the next statement we have initialized this value by the variable, by initialize the x variable by 10, so new value is 10. Next, watch point, new old value is 10 and new value is 20. So whenever the value of the variable will change, we will get the detailed information. Old value 20, new value 50, and function ends. So this is the benefit of having watch at any variable. End of the file has been reached. Okay, quit. So this is the way you can watch by using the watch points. You can watch any variable you have used in your code. Okay, even the pointers variable as well. So let us check one more program. This is the last program. See, this is a very simple code where we have allocated the memory, and at that allocated pointer we have stored some value and then freed it, and after that we are trying to dereference it. Okay. So what will be the output of same? Some random value. Let me run this code in GDB. Break main. Watch PTR. Sorry. First run. Watch PTR. Okay. We have allocated the memory. I will just print the PTR value. It is pointing to some this address. Okay. What is the value inside it? Simply print PTR, some garbage value. So this address pointing to this particular value. Let us next line. So there are the address changes. So this, now let us print the address again, and value pointed by this address 0. Complete is 0. Continue. And we are after counting we get some random value. Okay, quit. So by the watch by using this GDB we get to know that yes, we are referring to some invalid pointer. Let me see what happens when we run this code in ASAN, just to check what this report says. So output is heap use after free, because we have allocated the memory, set some value, then free it, then we are trying to dereference. So it is heap after use free error. Read of size 4 at this, which has already been freed. So this program can crash or have some unexpected behavior. That is the reason pointer bugs are so difficult to debug, because sometime we might get the result which seems to be proper but it actually not. Sometime we might see the address which seems to be valid but actually not pointing to the valid object. So we should be very careful when dealing with all these things. These are few examples and how we can debug. I have shown you. Let's move to. So to debug those issues, we have used tools used GDB. We have used watch points. We have used ASAN, address sanitizers. We have used Valgrind and code dumps. So just remember few of the things when we should use which tool. So GDB should be used when you need to check where did the program crash. So location, watch points to check who changed the value. ASAN, that is address sanitizer, to check what memory rule has been violated. Valgrind to check what leak or misused. Code dump, what happened in production crash. When we are in production environment, we don't have the debugging tools available. In that case, by using the code dump, we can debug where the crash actually has happened. So we can use GDB basically whenever there are crashes, segmentation faults, hang, given wrong value, or any step-by-step investigation are required. And for GDB, while we are compiling the code, use these flags as well. And address sanitizer can be used when we have to inspect the code where use after free, buffer overflow, stack overflow, heap overflow, double free or invalid access. To use the ASAN, just use this compiler flag. Valgrind we can use whenever we have to debug memory leaked, uninitialized memory used, invalid read write, or forgotten free. Valgrind tool simply you can use using Valgrind leak check and then run the ELF. Valgrind are usually slower than ASAN. ASAN is faster and better for active debugging, whereas Valgrind is excellent when we are checking leaks. Code dumps, we know that we can use it in the production environment. Simply set to generate the code dump, set ulimit -c unlimited. And watch points whenever you have to check what value changed unexpectedly, memory got corrupted, or who wrote that value. And always remember to use while compiling the code these extra flags. So these are the compilation flag we should use while compiling our code, so that we can get any type of warning beforehand, and we will be prevented from production crashes. So prevention compiler flag. As a system engineer, think when you see the pointer, it has some address. It is pointing to some address which should have proper ownership along with proper lifetime and validity. If anywhere any problem occur, means we will face the bug. Otherwise, if all four are correct, pointer, we will not face any bug. That's all in this episode, and that's all in this series. This is the last episode of our series. If you have followed this series from first to last episode, and if you have any doubt, any question anywhere, just do write it into the comment section, and stay tuned for the next series. Thank you. Keep learning.